All right, welcome back to Severe Weather. This is going to be lesson two. So the first thing to say before we get started, just a couple things. So we want to know what a dry line is. So dry line is just going to be a boundary between moist and dry air, and it's often indicated as a dashed line on some of the weather maps. But this is going to be really important in severe weather later on. So it's important to know what that is. And also, here's another thing to know that's a little bit counterintuitive, but also important to know. Um, when we have water vapor present, um, there's going to be lower density. Um, that might sound opposite. You might think there's higher density if there's water vapor, but there's actually lower. And parcels can rise easier in this case when there's water vapor present because the parcels are able to rise if there is lower density. So that's how that works. All right, now we're going to do a lot of this video is really going to be a review of some things from previous videos, but um, still useful to know. So there's three types of atmospheres that we want to know. There's a stable atmosphere, neutral, and unstable. In a stable atmosphere, we have warmer air above cooler air. So that kind of makes sense. And the reason why it's stable is that a parcel it's always going to rise if it's warmer than its environment. But we know that in a situation where the parcel can't rise, that's stable. So it's going to continue to rise until it gets to the warm air, and then it's cooler than its environment. Then it's just going to sink back down. In a neutral atmosphere, we have similar temperature throughout. Um, and so really the parcel's just going to stay in the same place. And then in an unstable atmosphere, we have cooler air above warmer air. This is often the case unless we have an inversion, which definitely can happen. But if we have, it's an inversion if there is warmer air above cooler air, because we know that typically temperature does decrease with height anyways. So that's going to be an unstable atmosphere. And the reason why it's unstable, once again, um, as the parcel is rising, once it reaches air that is cooler, it is warmer than its environment, so it's going to continue to rise. And a situation such as that is unstable. And this text here is just kind of what I just said, but that's going to be reviewed. Here are some images to show what I was just talking about. So this first one is a stable atmosphere. We can see that the parcel, as it's going up, it reaches a point where there's warmer air. So it's going to be warmer than this red, or sorry, cooler. The parcel is going to be cooler than its environment. So it decides to sink back to the equilibrium level where it ends up just being the same. Unstable, it's going to continue to rise until, or it's going to continue to rise because it's cooler or warmer than its environment. It reaches the cool environment. And so it is warmer than its environment. Because remember, the parcel itself is not what's changing temperature in these situations, it's the environment. And then, like I said, neutral atmosphere is just going to stay in the same. All right, return of the parcel trace. So the SKUT log P stuff is going to be very important in this course. So we're going to review some of this stuff. When we're doing the parcel method, if you recall what that is, uh, we're just assuming what would a parcel do as it goes throughout the atmosphere. And the way that we're able to determine that is because we have these rates. Remember, we have the environmental lapse rate, we have the dry adiabatic lapse rate, and the wet adiabatic lapse rate. And by the dry and wet adiabatic lapse rate, we're able to know what the parcel is going to do. What temperature will it be at once it gets to a certain height? The environmental lapse rate, we are able to know that's just telling us what is the environment doing as it with height. And we're able to determine that by the weather balloons that we send out with the radiosonde. And that is exactly what is plotted on this QT log P, if you remember. But there's two things that we have to assume when we're doing the parcel trace or parcel method. We have to assume that there's no compensating motions, meaning there's nothing that is filling in the air that is being moved. So this is not actually true. Both of these things are not actually true, but we just have to assume them for the simplicity purposes because we don't have as advanced of equations or technologies to depict what it actually is in reality. That, at least at the time of this video being made, that's not possible. So you just have to say, just assume that there's no motions that are accounting for what is occurring as the parcel rises. There are no like response motions. Then the second thing, you have to assume that the parcel will not mix with the environment and it retains its identity. That's definitely not true. Any parcel that's going up in the atmosphere, it will mix with the environment, but we have to just assume that it's not because otherwise we would not really be able to know what the actual temperatures would be. Um, and we have to know that we have an adiabatic process in this case. There is no exchange of heat between the parcel and environment. That's basically what number two is saying. It's an adiabatic process. In reality, as I mentioned, it's not. But we just have to assume that just so that we can actually use these equations that we've defined. Um, it's important to know your ideal gas law um, in this class. It's very simple in our purposes. You may have used this in a chemistry class, but for our purposes, it's pretty easy because the real thing to know is just the relationships between P, V, and T. So the equation is PV equals nRT. P, of course, is pressure, V, volume. N and R are constant in our case. N is number of moles, and that's definitely not something that's constant in our case. And R is a constant value in most cases, anyways. So you don't have to worry about N and R. And then T is temperature. So that symbol that's right here is means proportional, if you've never seen that before. But volume is proportional to temperature. What proportion for something to be proportional, it means as one goes up, the other goes up. As one goes down, the other goes down. If it's inversely proportional, then they do the reverse things of each other. So as one goes up, one goes down. As one goes down, the other goes up. But I'm only showing the proportional relationships. So as volume goes up, temperature goes up. As volume goes down, temperature goes down. Then also pressure is proportional to temperature. So as one goes up, one goes down. And volume is therefore inversely proportional to pressure, which means as volume goes up, pressure goes down. As volume goes down, pressure goes up. Um, then if we're talking about density, density is not in that equation, but we will have some equations that you will use, of course, in meteorology that deal with density. And you'd want to know that it's proportional to temperature and moisture. So as temperature or moisture increase, density does as well. The greater the difference between the environment and the parcel, the greater instability. Um, you have to recall CAPE. Now remember that a larger cape doesn't always mean clouds and storms. That's a common misconception. So you see a really big area in the skew log P that is cape, you might think that means, okay, there's a high chance of severe weather, there's a high chance of clouds and storms. No, that can be the case, but it's not always because once again, it is convective available potential energy. So potential energy, it's the potential that there could be, but it doesn't always mean that's what it's going to be. We of course look at other things that we'll talk about later in this course. Um, so the difference between the environment and parcel are determined by these rates that we're going to talk about more. So the dry adiabatic lapse rate, we're going to go into more detail than we did just in weather analysis one. The dry adiabatic lapse rate is oftentimes constant um, because it deals with specific heat of dry air and gravity, which are constant. We're going to talk about the equation in just a second. If the environment is in hydrostatic balance, which it typically is. So if there's any variance, it's very minor that it's negligible. Um, it means that we're going to have a decrease of 10 degrees Celsius per kilometer. So that's what this rate is. If we're going by this rate, then it is 10 degrees Celsius per kilometer. Now, how do we calculate the dry adiabatic lapse rate? You're not actually going to have to calculate it in this course, but it's useful to know the equation. It comes from the first law of thermodynamics, uh, which is that energy cannot be created or destroyed. And we see here that the um, specific heat of dry air times the change in temperature minus the specific volume of a parcel times the change in pressure equals zero. That's because that's basically saying, yeah, that energy is not created or destroyed. It equals zero. Um, then how to calculate the change in pressure is going to be negative density times gravity times change in height. And that makes sense because we know that those things are have a relationship to each other. All right, now the wet adiabatic lapse rate. Now, I also want to mention that some people call this the saturated adiabatic lapse rate or the moist adiabatic lapse rate. Those are synonymous, but I will typically use the WALR. This value is certainly not constant, um, unlike the dry adiabatic rate. This Using this rate begins at the LCL. So remember, if you don't remember, I'd suggest going back to watch the previous video. But um, if you remember, when we're doing the parcel trace, we at first are using the dry adiabatic lapse rate, but then we switch to the wet adiabatic lapse rate once the parcel is saturated, and that's at the LCL. Um, and then we just use that going up, going up, going up. And for a parcel that's warming, which would mean it's sinking, you always use the dry adiabatic lapse rate. Um, This is the equation for calculating the wet adiabatic lapse rate. It looks pretty insane, but it's really actually not that complex as it looks, but we're not going to actually calculate that in this class. That would be more of a thing for dynamic meteorology. So I will make videos on that later on, but you might have to wait until like August or September because I'm not doing that right now. Um, the oftentimes there can be a lot of variance with the wet eddy backlapse rate, but oftentimes it is around 5 to 7 degrees Celsius per kilometer. So, and next thing to note is we have condensation occurring at the LCL. When there's condensation, latent heat is given off because remember the MES FDC, that's a part of the FDC. So that's a warming process. Condensation is a warming process. And since it's a warming process, latent heat is given off. And remember, latent heat is phase change heat or phase change um, heat energy that's given off, heat that's given off. Um, and so this causes the parcel to cool slower. And this is why the dry adiabatic collapse rate is always greater than the wet. This equation that's right here is never going to be larger end up with a larger value than the dry adiabatic lapse rate. And that's because condensation causes the rate to slow down. So essentially, if the rate of condensation uh, is higher, then we have a lower, I know that says MALR, it's the same thing as WALR. Um, Lower rate, higher condensation, lower rate of cooling that occurs. All right, so now we'll talk about if we're in absolute stability, absolute instability. and conditional instability or unstable. Well, I don't. That's just conditionally unst. That's typos. Sorry, but you know what I mean. Um, so in this class, oftentimes I might say what we want or what is good, and I will refer that to as being a situation where we have severe weather, which I know a lot of people, some people would not see it that way. Like, and I'm not trying to sound like I want there to be bad weather, but that's what we're interested in this class. This isn't boring weather, this is severe weather. That's what this class is. So, that's why I make the happy guy with the thunderstorm, because that's what I want at least. Um, but absolute stability. That here's the order, and I came up with some things to help you remember um the order that they go. Just remember that it's always greater than signs. Don't flip the inequality. So greater than. So if we have the rate that's the greatest as being the dry adiabatic lapse rate, then the wet, then the environmental. That I say, dang, what? Exit, because I'm not interested. So dang what? Exit. You're not interested because it's just absolute stability. Ah, parcel ends up sinking. And why? I'll have a good visual a little bit later in this video to show why it's going to sink. And essentially, the temperature of the parcel is going to end up being less than the environment. And if it's cooler than the environment, it sinks. And why? How come the parcel ends up being um, colder than the environment? Well, it's because these these rates, the D and the W, um, are the cooling rates for the parcels. So if the rates are higher, then it cools quicker. So it ends up being colder than the environment. Once again, I'll have a visual to show that. So then absolute instability is if the order is EDW, excellent damn weather. That's what I say. Because if we have absolute instability, that's going to be a situation where the parcel is going to rise because if the rates that the parcel cools by are smaller than what the environment cools by, if the parcel rates are lower, then it cools slower. Parcel rates lower, it cools slower. And so that means that it's going to end up being warmer than the environment because the environment was able to cool quicker. See, the rate's the biggest. So the parcel ends up being warmer than the environment. And if it's warmer than the environment, it rises. And if we have a lot of rising motion, and you can end up having convection occurring, and clouds will end up building, we have a higher chance of thunderstorms and severe weather. Now, the most common situation, well, maybe not always most common, but a common situation can be when we have conditional um, instability. And the order of this is DEW. So another way to remember is that the environment is just in the middle. And of course, we know that the dry adiabatic lapse rate is always greater than the wet. So it's DEW. So I say, dude, I don't know. Like, because it's DEW, dude, I don't know. I don't know what it's going to be. It depends. Um, so that means, I think it's going to be too complex for me to just explain in words. So I'll just show you. I'll explain conditional instability in a second. But the last thing I want to say on this slide is for the biggest storms, the LCL will need to be closer to the LCF so that the parcels can rise on their own almost immediately. Once again, if you don't remember what those terms mean, you might want to go back to the previous videos. All right, now we're going to look at examples to actually show what we're talking about when we mean those three things. So here's our situation with our parcel. These gray things are two parcels. And why are there two? Well, because it's just showing you what the parcel's temperature would be if it followed either rate. So we're starting at 15 degrees Celsius. It goes up 1 kilometer. And here are two example rates. The dry adiabatic lapse rate is always going to be 10 degrees Celsius per kilometer. We already talked about that. And that's because the specific heat of dry air and gravitational constant are typically the same and if we are in hydrostatic balance. So this is always going to be 10. Now, this blue one, remember we said there was a whole crazy equation for that one, not always going to be the same. But for this example, it's 5. So I just want to make that clear. It's just 5 in this example. And I guess this honestly wasn't the best example because this 5 and 10 don't get mixed up with that. That just happens to be what the math ends up being. Um, but 15, so this tan line, all right, we'll do minus 10. So 15 minus 10 is going to be 5. 15 minus 10, or sorry, 15 minus 5. See that, why did I choose these numbers? Sorry if that's confusing a little bit, but this blue line is, the rate is 5. So we do 15 minus 5 to get 10. So those are the two possibilities of what the parcel could be. Let's say we sent up a radiosonde, weather balloon, and it determined, because remember it plots a red line, it determined that the environmental lapse rate is about 11 degrees Celsius per kilometer. So we'll plot that line as being to the left of the other two because it's a steeper slope. Remember, they're negative slopes because, um, and this is obviously not to scale because if it was 11, it would be a lot closer to the 10 line. But it's negative slope because temperature is decreasing with height. So it's a steeper slope, so that's why it ends up to the left of those two. It's a greater rate. The environment ends up being, we do 15 minus 11 to get 4. So the order of this is the greatest one is E, then D, then W. E, D, W, excellent damn weather, remember? So unstable. The order is EDW, excellent damn weather. That is what we want. So the parcel is going to rise in both situations. Why? Because they see 5 and 10 is greater than 4. If it's greater than the environment, it rises. So it rises in both cases. Oh, oh, never mind. That was supposed to happen. I thought, never mind. Okay, so now let's say instead the radiosonde found a lapse rate that was just 4. Then you do 15 minus 4 to get 9. So this time the environment is cooler than the parcels. And the order of the rates is the greatest one is Dollar, then the wet adiabatic lapse rate, then the environmental lapse rate. So the order is DWE, stable, because remember, uh, shoot, I have to remember what I said for that. Oh, dang what, exit, because it's not interesting. I couldn't remember my own acronym. Um, dang what, exit. I don't want that. So you say that it's a stable environment. And why is it stable? Because the environmental lapse rate is smaller than the other two. So this time, parcel's going to sink both. They're both going to sink because they're warmer than their environment or cooler than their environment. Oh, wait a second. Okay, sorry about that. There was a typo because 15 minus 4 is not 9. Okay, sorry about that. 11. I don't know how, I don't know. I'm not an idiot, I promise. So the parcels are cooler than their environment. Now it's right. 5 and 10 is smaller than 11. So both parcels are going to sink because when they're cooler than their environment, they sink. All right, the last possibility is if it's in the middle. Now then the radiosonde found a rate that was 7 degrees Celsius per kilometer. So that means that the environment that the radiosonde was in, that it detected, is 8. So the environment is 8, but that means that one of the parcels in one situation would rise and one would sink. So it's conditional instability. The order of the rates, we have the biggest rate is 10, then 7, then 5. So it's DEW. And that's, remember, dude, I don't know. So you don't know. It depends on the situation. If it is the dry adiabatic collapse rate, it's going to sink because the parcel ends up cooler than the environment. But in the other situation, it's going to rise because 10 is greater than 8. So those are the possibilities. So I hope that was a good review. Thank you for watching.